Welcome all to this sixth lecture of Principles of Statistics. At the end of the last lecture, we introduced a series of assumptions that we need to ensure that, that the MLE is consistent, or any MLE is consistent. And today what we're going to do is to introduce this consistency result and prove it. So let's just go straight to it. This is going to be Theorem 3, and it says essentially what I just said, and it's the following. So Theorem 3. So we have, let's take the usual setting. So let x1, x2, and so on be IID from model of PDFs or PMFs, f theta for some parameter space capital theta, and satisfying, of course, the assumptions that we introduced last time. Yeah, satisfying assumption A, and of course this means 1 to 6. Okay, so then we have that an MLE exists, so there is at least one, and any MLE is consistent. Okay. So what's the proof for this? Well, we've sort of spoken about it a bit already in the previous lecture in the past. But let's really formalize it properly. And so let's start, of course, with existence. So the existence is simple, right? So the MLE exists because, well, first of all, we have this normalized log likelihood. At least if we view it as a function of theta, then this is going to be continuous. Yeah, it's continuous, and this is, of course, because, well, I remind you maybe. Its form, so this is just 1 over n of the sum, over all of the data points of the log of fxi at theta, right? So this function is continuous, and it's so on a compact interval, right? On this capital theta, which is compact by, one of the assumptions, basically assumption A. Okay, so what does this mean? Well, that's yeah, okay. So MLE exists, yeah, I guess. I'm being a bit redundant here, but just so that I give it a name, yeah. And this is, of course, any of them in this case, yeah. So what we're going to show is that any of them will be consistent. Okay, so then if we want to talk about consistency, we need to say, well, what are we converging to, right? So let's then assume precisely that we have a true value that is generating the data. So assume that the data, the x1, x2, and so on are, they are, if you like, well, actually, we could just say x1 because they're all IID. So we can say that this is, this follows f theta for some theta equal to theta naught, some theta naught. So just the usual thing, theta naught in here, that is going to be, so this is going to be fixed, but of course this should work for every theta naught, right? Because we don't know it. So remember, the consistency will require that it's the convergence in probability to the underlying, generating parameter is, it happens all over the space, yeah? All over the parameters. Okay, so, and by the way, this has to be unique. Yes, this is where the uniqueness, perhaps not of the MLE, but certainly of the underlying parameter holds. Yeah? And this is from one of the assumptions that we had. Yeah, so from the identifiability of the model. Yeah? Okay, so this is unique. Yeah, as I just said, by the identifiability, which may be A5, I think. So then, okay, so what do we wish to show? Well, is what I just said in words. So we wish to show that theta n hat will converge under under the infinite product probability measure to theta naught. So this is under, well, or in probability, say, in p theta naught, and then the natural numbers probability. And this, of course, again, has to be for any theta naught that we choose. Yeah. Okay. So then, I mean, we sort of talked a bit about, how to do this. So we said, well, maybe, if we have convergence of this normalized log likelihood to its expectation, then maybe the maximum will not behave too badly. Okay. But that's actually not enough. Okay. So let me note that. So we need one of the assumptions, the last one, that will give us some uniformity, as we will see now. Remember that just simply by the strong or the weak even law of large numbers, what we have is that this guy is going to converge to this L theta, which I remind you that is given by this expectation, the log of x, and this may be x1 if you like, theta. So this happens for every theta here, and this is, as I'm just saying, by the weak law of large numbers. And then also remember that theta naught is the unique maximizer of this L, yeah, and this is from observation 1, yeah, that we had a while ago. So this is from the use of Jensen's inequality, if you remember, strict, in fact, yeah. Okay, so why is this not enough? Well, let's draw a picture, right? I mean, this is just basic analysis, really. If you put aside the probability aspect to it. So let's see. So if we have, if we have this. We take this to be this L, and then let's imagine that this is our parameter space, this compact capital theta. I mean, this is just the usual thing, right? So if you have, so forget about the probability statement that we have, after this node. So up there, the ln hat going to the to L. If you forget about the probability and just take it, imagine that the ln is not random, then, this is just saying that pointwise convergence doesn't give you uniform convergence. And this means that, if you had an approximation here, right, it's doing that. Well, yeah, okay, so this guy may not be too far from this theta naught, but it could be that we have, quite a different picture, and instead we have functions that are going to fluctuate a bit around here and then start sort of increasing, but they will flatten out as n goes to infinity, and so they will converge here, but the maximum will still be farther, will actually converge to the, say, the boundaries here, for instance. Right? So if we have, this pointwise convergence, then, even without the probability statement, it will not work. So what do we need? Well, we need some sort of uniformity. Yeah. So let's draw this again. So you should all be sort of familiar with these concepts. But what we're going to have to do now is to incorporate this probability statement as well here, right? So this is the capital theta, and so of course, if we have a band here, so that our functions are always contained there, and this band sort of shrinks, then that's great, yeah, and that will mean that essentially the maximum will converge to the maximum of the two, what I'm saying. Okay, so. Okay, so we need some sort of uniformity. Yeah, we said that. And so let's then state something that we will prove in the next lecture. So, this result is going to, as in the consistency of MLE, is going to depend on something that we'll see in the next lecture, which is the following, and is that by A6, the assumption A6, we'll have the following, which is that, so it's just what I've been mentioning. It's just uniform convergence in probability. Yeah. Okay. Okay. So then really, again, the idea here is just to say, well, what does this mean? Well, if we didn't have the probability statement, then we know that that's uniform convergence, and then we know how to prove it. So why don't we try to work on some sets that basically have very high probability and on which we have the usual uniformity statement? Yeah. So that's the idea behind the following. So let's, what this means, what this uniformity result means is that if we take the following set, so that's an epsilon, terrible epsilon, right? So if we define this probability or set of events, which is the supremum of those omegas in which the supremum of ln hat theta minus L theta is less than epsilon, then this is such that the probability and sorry, not that, so it should be this one here. So this one of an is going to go to 1. Yeah. So then it goes to infinity, and this is of course for all epsilon larger than 0. Yeah. Okay, so that should be sort of that should be clear to everyone, because that comes from this convergence in probability that we stated here. Yeah. Okay, so now once we can work on these sets, which are giving exactly the sort of band that we wanted for some epsilon. So maybe let's just say, and so we work on an epsilon for epsilon to be chosen, yeah, or to be confirmed. Yeah. Okay, so once we have this, yeah, we have the band, and so now that we have the band, it's just the usual proof from analysis. Yeah. So what we want to do, well, we want to look at a region. So if we have a delta here, so let's say that's theta naught minus delta, and then this is theta naught plus delta, then fix the delta, and so if we make the band, this band here now, maybe let's draw it in a different color, make it red. So if we make the band thin enough, then what will happen is that, and that should be parallel to the other one, by the way, even though I have this sort of wiggly writing. Okay, so if we, oh no, which one's this? Is that right? Oh no. Okay. Okay, well, we'll have to continue on this color, I guess. Yeah, it's that one. Okay. So then if we have this band, what's going to happen is that, if this is very, very small, then essentially the maximum that this ln, this wiggly function that would be around here, the maximum that it takes away from delta is going to be less than the maximum that it will take, the value that it will take at theta naught. Yeah, so if we make that thin enough, then essentially we will have, that we can control that maximum. Okay, so the maximum really is attained really within this delta distance from theta naught. Yeah? So that's, in words, what I want to say is that let's consider so for all, well, or for I guess for a given, for delta larger than 0, and this is going to be fixed or arbitrary, even just take fixed and arbitrary, so arbitrary but fixed. We define this set to be the set of thetas that are away from theta naught by at least delta. And so then we wish to show that our estimator will belong to this guy minus this guy. Yeah? So it will be basically within distance delta. And because, the delta is arbitrary, if we can show this for any delta, then clearly, so if we can show that it is contained there, for n large enough, given a delta, then that will mean convergence, right? So that's just the usual game. Okay, so we wish to show this, and of course, this is going to be with high probability. Yeah? So we cannot just expect things to work deterministically. So this high probability will be essentially this AN that we have, yeah? The high probability set in which this is happening. So then let me make a claim, and this is what we're going to, and this will basically prove the result. So the claim is following, and is that, the supremum is what I said in words already, and it's that the supremum over this guy, away from delta of this guy is going to be strictly less than that, which with the value at theta naught, which will then mean that, of course, the maximum of the normalized log likelihood should be attained, within a delta of theta naught. Yeah. Okay, so how do we show this? Well, we look at the sup of this ln theta. Then, by the triangle inequality, this is simply bounded by the sup over this guy plus the sup again over this of the difference in absolute value between the two. Yeah. Okay, so that should be simple. Yeah, to follow. Okay, so we have start with, well, or we can say, well, let's leave this first term out for a second. And that's actually not going to be hard to work on, right? Because that's a deterministic function. And so now what about the supremum? Well, we are working on, we said that we work on AN, yeah? And so AN, I remind you, that is, set where these, we have this band of epsilon. So then this means that, this is less than epsilon on this AN, yeah? Okay, so then now let's work on the first term. Well, what's the first term? So this first term, yeah. So this first term is going to be L delta bar, if you like, for some theta delta bar. Why is that? Well, because this guy is compact, right? And of course, L is continuous. So you attain, so the maximum is attained within the set. So of course, this guy, of course, belongs to this. And this, by the uniqueness, so by, because this theta naught is the unique maximum, right? this we saw before. Okay, so let's collect what we have here. So then, what we have therefore is that this is less. So this is less or equal than. Actually, this should be strictly less than epsilon, because on an epsilon, so excuse me, but so this, so here, this inequality up here should not be equal, but rather just strict, because that's from the an. Yeah. Okay, so now again we have this strict, and this is going to be just simply this L theta delta bar plus epsilon, and this is now the usual game, right? So we need to choose this epsilon small enough so that this band is small enough. And what is small enough? Well, the choice generally is just halving the difference of this maximum value, right? And this. So that essentially what we get is that the right-hand side here is bounded by this quantity, which is just a bit less than the maximum. Yeah. Okay, and then once we have this, well, it's just a matter of just collecting again the results that we are getting. So this is then saying that we have L theta naught, so let me subtract now following quantity, so ln at this theta naught, and then we have the minus epsilon, and we also have this ln theta naught that I've added, well, that I've subtracted before, and then, very simply on an, so an, remember, is, on an, we have that the difference is bounded by, the absolute value of these two guys is bounded by epsilon, and so of course this guy therefore is going to be less than 0. Yeah, it's going to be negative, and so this shows the claim. Yeah. Okay, so now that we have shown the claim, as I was saying, it's now immediate to say that therefore, the maximum of the ln, which is this guy, it cannot belong to this, i.e., so what we have is that this maybe capitals. So then what we have is that this theta n belongs to this, and then and therefore an epsilon is contained in the set of omegas that give you that this theta n hat minus theta naught is less than well, in this case it would be delta. Yes, of course. Okay, and now remember that this an, so remember that the probability of this guy, well, this will be bounded by, sorry, this is not the double BP, but rather the other one, so this one, an, therefore, is less or equal than the probability, it's not n of, these brackets up here, and this goes to 1, and therefore this goes to 1. Yeah. And this is for all delta arbitrary. Yeah. Remember that we said that here when fixing the delta and introducing the delta. So delta arbitrary. Okay, and this shows the result. Yeah. Okay, so let me maybe remark that we've only used this sort of continuity here. Yeah? So if you have more so simpler proofs to exist, if if we have essentially with more structure, under more structure. And so, for instance, if we have that this normalized log likelihood is differentiable rather than just continuous with a unique MLE, basically, well, or a unique maximum, which is this guy, MLE. And we also have, well, and so the theta is going to be, by the way, maybe let's just write straight away, this guy. Maybe I should have written this earlier, but anyway, that's fine. So it's here, and it's not necessarily compact. Okay, so this can be useful as well in the case in which we don't have this compactness, like it could be on the normal or in the toy example of a normal distribution, but it mean just belonging to the whole of R, for instance. So we have this, and we also have convergence in probability of the derivatives to the derivative of this guy, and of course for all guys here, with where this L or L prime, if you like. It has to be, the L prime has to be continuous, of course. It's continuous. And has a zero, unique zero. Yeah? Unique zero theta naught. Yeah? So then you get consistency. So that's 2%. Right. Okay. Okay. And this is, by the way, so this will be. I think this is the first exercise in example sheet 2. Okay. So let me now talk about. So remember that we left this uniformity result for the next lecture, but let me introduce a few things before we actually introduce this result. So what we're going to need is what is called the uniform law of Latz numbers. So why is that? Well, remember the law of Latz numbers. What it is saying is, you have a sample mean, and this converges to its expectation. So sample mean is just simply, the mean of some random variables. And, what we really have here is actually, if you fix a theta, if you fix a theta here, then this is really, the quantity that we would see in the law of Latz numbers. And so by having, by considering theta in some space, which could be uncountable, then what we really have is an uncountable number of random variables that we're trying to show that they all converge, right, in probability. So that's why it's called the uniform law of Latz numbers, what we're going to need. Yeah. Okay, so let's then, consider, let's build up gradually what we want to get. So let's start, simply by looking at, so let's say, so digression. Digression. So we have the following. So this is the uniform law of Latz numbers, that I was talking about. So okay, so then let our x's x2 and so on be IID copies of actually doing that. I don't think so. So these are IID on some sample space within RD, okay? And let also have, let H be a function that goes from the sample space to R, and it has to be measurable, okay? And such that, well, yeah, okay, so that's fine. So let's yeah, okay, so then, okay, so such that, so I do want it to satisfy some measurables, and such that the expectation, this x1, for remember these are IID, so we can just assume any of them is bounded, so it's finite. Yeah? So then what we get, of course, then is that the H x1, H x2, and so on are IID, and by the law of large numbers, or by the weak law, depends which one we want to use, but by, let's say, strong law of large numbers, then we get that the sum for mean, these guys, the images here, of course, goes to H, yeah, if you like, the expectation here, the gain of x1, if you like, almost surely. Okay, okay, and this is, if you like, under this PR that we introduced, sort of, so the intimate product probability measure. Okay, so what about if we have several functions, but but finitely many? So if H1 to H capital N are a family, or is a family of such functions, okay, that, and this is finite, by the way, so n, of course, has to be less than infinity, okay, then let Aj be such that, and the PR, its complement is 0, is a null set, the complement, and such that, the above holds for the jth element, but maybe an absolute value, which is just the same, essentially, so this would be the jth, and this is x, sorry, this should have the expectation, and the, well, not and the, that's that, yeah? Such that this converges almost surely, yeah? Okay, that such Aj, of course, exists, yeah, from the convergence and probability of each one, or almost surely, sorry, from each of them, from the strong law of large numbers applied to each of them, yeah? Okay, so then, it's just trivial to say that if we look at the maximum for j less or equal than n of this quantity, then this will converge to 0. Sorry, that should have a 0 on A, which is the intersection of all of these guys. Okay, and of course, so where it's just trivial to say that the probability, so PR, of the complement of A is, in this case, it would be the union of the complements, and so this is less or equal than the sum of the probabilities of the complements. Yeah, and remember, the complements are 0, and this is a finite sum, so this is just 0. Yeah. So then what we have, is that, we have the convergence. So this means that, the maximum over these guys does converge almost surely. Yeah. under this PR. Yeah. Okay, so that's, I mean, that's sort of to be expected, right? Because we have finitely many. So really the question is, you know, when we have infinitely many, then what can we say? Even uncountably many, right? Which is what we really need, as I argued earlier. So, okay, so for general class, I'm going to call this sort of calligraphic H of functions, or of, I guess, yeah, okay, the same as above, yeah, such functions. This will be, you know, functions that are going from here to here, measurable, you know, finite, absolute value. Then let me introduce a concept. So we say that a family of brackets what is bracket? We'll see in a second. So family of brackets HJ bar J from 1 to some finite number, so it can be just capital N. So then this covers this calligraphic H if for all H in the space we have a bracket in which it is contained, essentially. Yeah? So there exists a J such that, let's see, so HJ here is less or equal than HX, less or equal than HJ bar X for all X in our sample space. Okay, so that means bracketing. Yeah? So you just, you know, you have your sandwiching any function basically between some bracket. It has to do so for every function, so it just covers the whole space. Yeah. Okay, and by the way, so I mean these guys need not be in this calligraphic H, and without loss of generality, we have that, you know, they are pointwise satisfying this, because otherwise it's just empty, the bracket. Yeah, so that's, okay, so let's now state a result that basically is an intermediate result to the one that we want to get. Well, as in this is the uniform law of large numbers. That's the one we want to get now. But I mean the one that we will need. We need it before in the other proof. So theorem, as this theorem is proposition. So proposition 2. Okay, so for all epsilon greater than 0, let's assume that there exists a finite number, or n many brackets covering H, and such that they satisfy the following two conditions. So the absolute value of this, if we take the expectation, is less than infinity, so it's finite, and so is the upper limit in the bracket. Yeah? And then the second is that we wish the difference of the two in expectation, in absolute value and expectation, to be bounded by epsilon. So they're not far in this sense here. Yeah. Okay. So if we have this, then then we get essentially what we are expecting, which is that the supremum over this calligraphic h of these, the sum or the sample mean. This may be better to say I. 1 to n of h of xi minus its expectation converges to 0, and this is of course almost surely under this guy here. Okay, so we'll prove this in the next lecture, and we'll then introduce the result that we used during the previous proof of consistency FMEs. So I hope you enjoyed this lecture, and I will see you again on Friday.